Today we're going to start talking about hypothesis testing. So one major way that inference is done is reporting confidence intervals. So telling you what the likely values of parameters or population characteristics are. And the other way it's usually implemented is by conducting tests about those same parameters. So we're going to look at the setup for hypothesis testing and then look at randomization to evaluate this, right? To evaluate whether a null hypothesis seems reasonable given your data, or you should throw that out or not. Right? The homework, I changed the due date to next Friday instead of next Wednesday. That's the Friday before spring break. I believe we'll cover enough material between, on Monday to do the homework by Wednesday, but on Wednesday we'll have time to do some more questions and a few more examples to help clarify things with that. So let's do on Friday before break. Right? So the idea that we're interested in studying a population, gathering data to say something about what the population characteristics are or what the average effect of something is. Right? And so we have our population, and we're going to concentrate today on the average population mean. And for that, we get to evaluate that. We're going to take a sample. We'll take a random sample and get some different measurements and summarize those with X bar. And so one way of saying things about what mu is, right? So we want to do inference and answer the question is what is mu based on our sample. And one way of answering that is with a confidence interval. Right? So you can do a confidence interval for mu is one way of answering that question. And so that would tell you the likely values of mu, like X bar plus or minus a couple standard errors should give you a picture of where that is. But many times a hypothesis test can be done where you have some hypothesis test. HT is my abbreviation for hypothesis test. Right? Often you're interested in certain values of the parameter, whether they're reasonable. Often this is in relative to change. So we often is going to set up a null hypothesis and an alternative and evaluate which one of these seems consistent with our data. And it's usually done a little asymmetrically. That there's a H0, which is called a null hypothesis. And in this one, in this case of a mean, we're going to say that the population mean is some value. This says that the population mean is a specific value is some mu sub 0. Right? And the null hypothesis usually has the interpretation of no difference or no change. That everything is just like the general population, or it's like it was last year, or it's under some general conditions, and that's just the way it is. Usually this means no difference. No change, kind of status quo. And usually that mu sub 0 value is known in the context of some field, right? And it has some meaning in the thing. The other hypothesis is called the alternative. Hypothesis. And it can say a number of different things, right? So one thing it can say is just that is not true. When it's not equal, it's called a two-sided hypothesis, two-sided alternative. This is the letter A here, so this will be clearer, right? And so that alternative just says it's not that value. Some things have changed, some things are different. It's not what you expected. There's a difference somehow from the null hypothesis value. I'm going to go out of that and come back. Is that going? No. Oh, wait, you thing. Is there a way to undo that? Anyway, I'm just going to leave it there. So that says that there is a difference from the null hypothesis. Right? And so sometimes that's done, right, in one of these contexts. Maybe this, you're doing a drug to lower blood pressure, right? So this could be the average reduction in blood pressure. Blood pressure, right, for the standard drug. And now a manufacturer has come up with a generic version of it, trying to sell it at a cheaper price, right? And so you might want to see, is the average reduction in blood pressure for this cheaper version, for the generic version, equal to the same thing as the standard drug, or is it actually different? So this can say the average reduction. Okay. Average reduction is not the same. But this kind of setup of setting up hypotheses can apply to a whole number of situations, and it's in the context of the thing you're studying. Right? So let's say we're in the study of education. And let's say P is a parameter that is the percent of children who are proficient at their reading level they're supposed to be at for their age. Okay. And there's some kind of standard thing, the current percentage is PC, some value PC, 90%, 80%, 70%, something for the sake, right? And then changes come in. They consolidate schools, cut budgets, do different changes. Right? Changes happen. 3 years later, we can ask the question, have these changes, these budget cuts, consolidations, and changes, have they lowered the percent who are proficient at reading level? Has the series of change reduced proficiency? Oh boy, this was funny today. So this would be set up a null hypothesis. Say this value up here of P sub C was something like 70%. And now let's let P sub n equal the new rate of proficiency. Is that new rate equal to what it was before, or is it less because we've cut budgets, cut staff, cut extra reading professionals and extra help in the schools to save some money? What would you want to set up as a null or alternative hypothesis?
Percent in proficiency stays the same.
Yeah, so if it's the same as before, we'd say that the new rate is this old one of 0.7. Because before it was 0.7, and if at the new time period after these changes has it stayed the same, setting up the alternatives, whether it's not equal to something or bigger than something or less, that's really in the context of what you're looking at in the problem. In most of our problems, if you do what you said that it's not equal, that'll be fine. A lot of the calculations are the same, whether you do it greater than or less than. It's kind of at that one last stage of determining what we'll call statistical significance, that there's a little difference. But this one has a change reduced, even less than 0.7. Right? So because this is saying, has it reduced it, I'm going to have the alternative saying that it's less. And so we're going to get some data on the schools and the children in the schools, and then try to assess has it happened? Has it dropped? For advocates for putting the money back into the schools and getting those extra reading teachers in there, we're not happy that it's decreased, but we might want to prove that it's decreased to justify, right, arguing that the changes to cut money and cut resources were bad. Right? And so you could apply that to a huge number of scenarios. So what we're going to do as a general framework is we're going to have hypotheses about a parameter. So we're going to do something with a mean here, so I'll write it like this, and initially we're just going to say that it's not equal to that, so we're going to look at that scenario. This O is 0 value and this is A, right? And then we're going to get data, and we're going to calculate a statistic, some summary of the data. And we're going to use that, our summary of the data in this case is going to be X bar. We might also have the sample size, we might also have the sample standard deviation that we'll compute, but the principal one is going to be X bar. And we're going to compare the X bar that we have to the mu sub 0. And a key aspect of this comparison, immediately we'll see, is X bar bigger than or less than, or does it seem kind of different than this hypothesized mu sub 0? But is it any more than chance? Has it really deviated, or have we just got a random sample where there's a little bit of difference, but nothing's really changed? And so what we're going to look at is the sampling distribution, the probability distribution of X bar under the assumption that the null hypothesis is true. That the null hypothesis So we did some work with probabilities, talked about sampling distributions of statistics, distributions of X bar. We use that in confidence intervals, and it comes in here in the sense that the only way we'll know whether X bar is really different statistically, bigger, more different than just a random variation than from mu sub 0 is if its sampling distribution just does not look like it's consistent with the null hypothesis. So there's a connection to probability. And this sampling distribution, we're going to see a picture a bunch of times on Monday, that if the null hypothesis is true, that the sampling distribution of X bar so here's the values of X bar on this axis. If the null hypothesis is true, right, that it should be centered right there at our hypothesized value. Right? So if you get so if that's true, you're going to get where your X bar is going to be. Your X bar is going to be kind of close in here, right? And relative to the spread, the variability in X bar is centered at that point. If we're close by, it's not going to be so extreme. But if our actual sample X bar ends up being kind of out there, that's kind of unusual, right? If the distribution really was supposed to be here, we got something way out of the tail, or way out here, right? And so the business of hypothesis testing is quantifying that. How do we decide how far is too far? More than a couple standard deviations, standard errors away, plus or minus 2 standard errors from here is going to be part of the answer, one form of the answer. If the probability that you're at this point or further out is quite low. If you're out kind of in that 1% tail or 2% tail, that's kind of an unusual thing to happen. So if the null hypothesis says we're here, and this is the sampling distribution, and we get an X bar out here, it looks like we've seen something really unusual, quite rare, very inconsistent with mu sub 0. Either that's happened randomly by chance, and we got kind of a rare event, or maybe mu sub 0 is just wrong, right? Maybe the sampling distribution has shifted over this way, and mu sub 0 we should give up on this. Stop pretending that that's the truth, and say, well, no, oops. Great, let's see, come on back. You could almost have like a training session for these things. In any case. So let's look at some data and what I call the. Does anybody have a copy of the handout? What I call randomization approach to this. So we're going to look at a data set on admissions to ICU, intensive care units, and these are adults. Here are their ages for these people, and in this data set, studying their characteristics of who gets admitted, their sex, male, female, race, different services. They come in with cancer, renal problem. They perform CPR on them, systolic blood pressure, and so on. So quite a few different things. Were they conscious as they came in? So that's the data set, and there's 200 rows of people in this data set. So I'm going to read these data into R. Right? So they're sitting here in a directory for me. But I need to, my global environment up here has nothing in it. This little LS, there's nothing, there's no object there. So I need to get that ICU data set into here. It's a CSV file. If I see it here, I want to make sure that R is looking there. So, you can set that place that I'm looking there as the working directory. Or I could go up here to the session and choose a working directory. That would be that place where that file is. But in any case, I need to be able to see that file. There's a command called list.files. And so look, here it is. ICU admissions is here. So I should be able to read it in. It's a CSV file, so that does it. This header, that T means true. There are header rows in that data set. So I read that in, and now ICU is up here. And this ICU, if I just click on it, it shows me the data. This is not really a place where you can edit things, so I'm not going to keep that, but it's there. It has 200 rows, 21 variables. These are the names of all the variables, so if I type that, it has all those in there. I'm going to focus on age right now. So this is the distribution of the age. But I'm going to imagine that somebody has said that the average age is 50. The average age of people coming into ICU is 50. So that somebody makes a statement, so the newspaper makes a statement, or an administrator makes a statement, or the budget planning, and they're saying that the average age in the ICU for adults is 50 years. Is that a reasonable statement? So we just want to use data to evaluate this claim. Where did this come from? Maybe an industry report, maybe that's what it was 10 years ago when they did a big study. Maybe some insurance carrier says the average age of the people who insures is 50. Is it the same as people coming into the ICU, or as that insurance company, or is it different? It's a big, important question about how the people that are covered by insurance might differ from the people who are not. So maybe the average age of adults under some insurance plan is 50, and is that what it's like in the ICU or not? So as a null hypothesis, we're going to set up a hypothesis about well, we're going to set up, is it 50? So is the average equal to 50? You can either use the Greek symbols, or you can say the average age, 50 years. When you write reports or write for a company or something, you don't really write H0 equals something. You write in plain language that the average age was hypothesized to be 50 years. And as this, is that reasonable? That just is that it does not equal 50 years. So average age isn't 50 years, right? We're going to look at our data and try and assess that. It's always good to look at your data a little bit to see what they look like. Right? The summary of the age, the average age in our sample was actually 57.555. It ranged from 16 up to 92. Maybe they allow 16-year-olds to injure themselves into the ICU when they're not, counted as children if they come in under their own recognizance or something. The oldest age is 92, but the average is 57.55. That looks bigger. Okay? But with a sample of size 200 with this variability, could we actually get 57.55 when the real average is 50? Could that happen by chance, or is it kind of surprising? I'm going to attach the ICU. So that's an R little command. So I don't have to type that ICU $ anymore. I can just type the variable names. I can just deal with age. So is that plausible? Let's look at the data. Here's a histogram of the data. Anything kind of interesting about that histogram of the ages of people coming into the ICUs?
The majority of the people are actually in between ages 60 and 80.
Yeah, so a lot, 50, 60, up to 80 or so, kind of an older age coming in for medical conditions, right? But there's a group of, younger, 15 to 20, 20 to 30 that are coming in that, I don't know, it's just accidents, whatever, something's happening. The average for the data, 57 is here. Right? The average that we're hypothesizing is here, 50. Right? You can put little nice little, right? So the blue is the hypothesis value, and X bar is that. Right? And these are the data. So it's not a sampling distribution, it's the raw data. But we're trying to judge is that a real change or is that unusual? If you look at these are the actual age values, if you sort them, right, that are in there. So you see all the 50s and 60s and 70s, a few 90s. A stem and leaf plot, in this case actually, kind of looks like that histogram turned on its side, but kind of reasonable to do it with this number of data points, maybe not much more than 200, and 2,000 would be wouldn't work so well, but kind of gives you a nice picture of that. And so we're going to look at the sampling distribution of X bar, focused at X bar, and at the sampling distribution focused at 50. So X bar is roughly normally distributed. Even though the ages aren't quite normal, and they have that kind of peaks and things, right? We know that X bar is approximately normal. Right? So what is the sampling distribution of our sample statistic X bar? Well, the average of X bar should be this mu parameter, whatever it is. It's standard deviation of X bar. If the standard deviation of X individual was 60, or sigma, it should be sigma over square root of n. So it gets tighter, it gets more precise as you get more samples. And by the central limit theorem, right, X bar should be approximately normal. Approximately normally distributed. But the variability in X bar in terms of how many standard deviation units it should be away from its mean, is roughly described by the normal pretty well. So we're going to draw that picture of that normal distribution at different means with kind of an estimate of the standard deviation of this sigma over the square root of n. So if we do that, the averages are going to not really vary between 20 and 100. It's going to be tighter. So I'm going to do it between 40 and 80. Like this little sequence command, right, gives me numbers. Maybe I won't do it all. So the sequence from 40 up to, say, 45 going by 0.1s gives me 40, 40.1, 40.2, etc. So it gives me this little sequence that I might like. I'm going to do that up to 80, so it's a little bit longer. And I'm going to plot this sequence, what I'm calling x, from 40 to 80. And the height is going to be the normal density. That is the normal sampling probability density function. Right? And so that thing looks like this. It's a normal curve centered at, I've centered it at 57. And that's the standard error. That's like the spread. That's how spread out the x bars likely are to be. And I've made it a nice line. That's a little L there, type equals line. But I've changed this label up here to be f of x. So it's the probability density function. The average 57 that I've used right now, this mean of age, right, that thing there, the mean of age is, oops. I was just going to copy this. I'll just run there. It's 57.5, so that's where that average is. Where's 50? Is 50 kind of in the ballpark there? Right? So there's 50. A nice little title below that. Right? But, so if the sampling distribution is centered around 57, that's kind of the spread of x's that we're supposed to see. But our hypothesis of 50 is kind of off from that, right? And so this would look to be a little bit inconsistent with each other. In hypothesis testing, we kind of concentrate on the null hypothesis, right? So if the null hypothesis is a mean of 50, is we're going to look at what would the sampling distribution look like if it was centered over there at 50. If it's 50, here is the average at 50, right? The probability distribution, the normal would be centered right there. Where does our x bar actually show up? Our x bar actually shows up over here at this red line. Right? So does our claim that, that the average is 50, does that look like a reasonable claim at this point? X bar looks kind of far away, right, from this. So a lot of what hypothesis testing is looking at the distribution under a null hypothesis and then comparing it to the values you have and figuring out a quantitative way to summarize how unusual is what you've seen. Right? And one way to do this is called randomization. It's kind of like a bootstrap where you reuse the data and generate new samples. To do that, well, the original data weren't centered at 50, but we need to adjust them. Pull them over so that they're centered at 50. There's different ways of doing this. This is one way that's done. To move the data over to an average of 50, you can subtract the average that you have and add 50 back in. So that will move the data over to 50. So if I do that and adjust it, I call a new thing, age at 50. Right? And the average of that is 50. And I've just shifted all the points over. And what we're going to do is do a bootstrap distribution of the averages with those adjusted data. Right? Those adjusted data are consistent with the null hypothesis, and we're going to see how that comes out. If we had 1,000 samples that really were consistent with the null, what would the averages look like? So do it 1,000 times, set up a placeholder to hold my things, and then go through this loop. Right? Each time I'm going to take my adjusted data here, and I'm going to pick 200 times with replacement. Right? So each sample is going to be picking from my adjusted ones, all those different times, and then taking the average of that. So this little loop here implements that. And this is the histogram of my 1,000 samples. again with the same range. And just like the continuous picture, right, the red one's over here and the blue one's right in the middle of all those. And the blue is the hypothesis, and our adjusted simulation, this randomization under the null hypothesis, is back over there. But our hypothesized value is outside. Does it look like the red line could have come from the null hypothesis? No, it doesn't look like it's possible at all, right? It's completely outside of the range of things that are likely to be done. We can quantify what percentage of the samples are actually bigger than this value or more extreme. And it turns out there's none of them. The bootstrap is less, the bootstrap values, those 1,000 values. So these bootstrap values, if I show you like say 10 of those, right? These are 10 averages from different random samples. They're all centered around 50 because they were adjusted so the data is centered around 50. But all of them, all 100% of them are less than that. And none of them could, in 1,000 replications, could I possibly achieve anything that was that high. That suggests that the average really is not 50. It's in fact much higher. And so in this case, because the randomization can't produce any data, any averages that are close to that, we will reject the null hypothesis. So in this case, about the conclusion about age, and conclusion about average age, the randomization distribution, I'll phrase it this way, the actual value of X bar, which is 57.5 or so years of age, is very extreme in comparison to the randomization distribution or you just call it the sampling distribution. Of X bar if the mean were really 50 years. If 50 years were true. So we got that. We adjusted the data over to 50. And we simulated what X bar would look like. And our actual one is way outside of that. So either something bizarre has happened, we've had a funny sample of some case, right, something really quite unusual, less than 1 in 1,000, much less than 1 in 1,000, or maybe 50 is not right. And if this really was a random sample from the population, and you don't think there's other major problems, then probably it's the average age going into the ICU actually is higher, which will impact, the types of cases that come in and all that. So that's hypothesis. A lot of the statements about hypothesis conclusions have this kind of what if flavor. Right? What if the mean actually were 50 at the null hypothesis? What would we see? If we don't see something consistent with that, maybe that our what if scenario is just not right. So it's a little bit of a reversal. You kind of set up a hypothesis and then show that it's wrong or not. Right? Let's look at a second example. Their heart rate is measured there. Right? You can measure heart rate, blood pressure, any number of other things on patients. Heart rate is measured, and for men it was 100.3, and the average for women was 98.1. Kind of this S-apply thing is a little way to get that automatically. The split thing will split the data between the zeros and the ones that are in the sample. And the split apply, this S-apply thing, will compute the mean of each part. So it gets the means at once, just kind of a little command. And so, we could ask the question, are the heart rates of the men and women who come into the ICU, is it different by group? Or are they the same? What are you going to set up as the null hypothesis? Doing something like this. So men versus women. And heart rate. So what parameters are involved? Do our hypotheses and our confidence intervals always about parameters, population characteristics, general characteristics of groups. So what are two parameters? Two parameters here. Yeah.
Heart rate,
Heart rate. Whose heart rate?
men and women.
Yeah. So there's the average heart rate for men, and there's an average heart rate for women. Average heart rate. For men coming into the ICU, and the average heart rate for women. And we want to set up a null hypothesis. And the null hypothesis usually means no difference. That kind of gives it away, doesn't it, right? We're going to say that the mean of the men is really equal to the mean of women. Right? No difference. And I don't know whether men or women who come into the ICU tend to have a higher heart rate or lower heart rate, or things like that. But we can start out just saying that they're not equal. And heart rate averages between the two populations coming into the ICU is just different. In a lot of studies, we will look at cases where we have a clear indication, if you have a drug that's supposed to lower blood pressure more than a placebo does, right? Then we're going to say that the average decrease is less, than the other one, right? So that will be kind of a clearly one-sided. You clearly have an indication of how things are in, that one direction is good, and you hope for that, or that you're trying to detect. But if it's not really stated, then you can do two-sided. So we're going to look at, we'll have different data here, right? We have an X bar for men, and we have X bar for women. If there's no difference, translates into you can take the difference between the two. And I would say the difference is 0. The alternative hypothesis says that the difference is not 0. And so we're going to get data, right, to evaluate this. And we're going to look at the sample differences of men versus women. And that's not going to be exactly 0. We don't expect it to be exactly 0, but is it significantly far from 0? Is it more away from 0 than we would expect just by chance? Right? You could have done this, flipping these, women minus men, and then you would just flip it all the way along,
Yeah.
and have to keep consistency.
If you wanted to calculate the sample difference, wouldn't you have the absolute value of those two?
You
So
could,
just
right.
Its positive value.
Yeah, you could look at that and kind of look at one side. Well, we'll deal with that by looking at the, is the difference really big or really small? When the alternative is two-sided, you really look at a difference in either direction. So kind of implicitly, we do that. Some books phrase it as an absolute value as well, but yeah. So if there's a difference, big or small, it's not going to be the same. Right? So in this case, we get those. Here's just a box plot of the data. There's a fair variability in the individual measurements, right? Individuals have heart rates, as low as 50, as high as, well over 100. The medians are here. I can put little horizontal lines in here, right? That are the two means of the group. That's 100 and 98. Does it look like there's much difference between these heart rates averages? Not a whole lot, right? It doesn't look like it. It looks like there's a lot of variability. If this was based on 200,000 people, though, even a small difference like that might be significant. It all depends on what the sampling distribution looks like. Does the heart rate different by sex? let's do our randomization. So we're going to adjust the data to be consistent with the null hypothesis, right? We're going to make the data look like have an equal average of the two groups. So to do that, we're going to just copy heart rate over to a new variable. And if the sex equals 1, I'm going to adjust those numbers. And sex equals 0, I'm going to adjust those numbers. And I've made this little adjustment where I've made it so the averages are the same in the two groups. Right? And so it's not much of an adjustment. So it's just tweaking the numbers a little bit because there's not much going on here. But you see that little, my little animation here of what's happening. Right? So now I've adjusted the data. I'm going to bootstrap it. Right? So in this case, I'm going to take a random sample of the men and a random sample of the women and look at the differences between the men and the women in these equalized groups. There's a few ways to do that. I'm going to set up a new place to hold my results called boot2. This is the second example. And I'm just going to randomly pick data, just randomly resort the data. And then the ones that used to be labeled as ones, I'm going to take the average of those. And the ones that used to be labeled as zeros, I'm going to take those. And if it's really true that there's no average, right, then it really shouldn't matter how I associate things in there. Right? So this is the randomization. I can randomize this and get a new data set, and it's consistent with this null hypothesis of just equality. So let's do this. Let's run it. Here's the histogram of the average differences. Here's the histogram of the actual x bar minus 1 minus x bar 0. Here's the null at 0, right? And a little subscript right there. So does that look like the red one there, the actual one we got, the difference of about 2? Is that something we could plausibly get without much concern or a surprise if the null hypothesis is true? Okay. That doesn't look surprising at all, does it? Right? The null hypothesis is here at 0. Just by random chance, we can easily get things between -5 and 5. And it's not so unusual. We actually got about 2 as an average difference. And so it's very consistent with 0. And so we wouldn't be surprised, and nobody, I don't see any reason based on these data to give up on the idea that it's equal. It doesn't seem to be significantly different. The percent of the randomized things that are actually bigger than our actual number, there's about 25% of the random generated cases are bigger than that one, and about 75% low. So, 25%, that's not an unusual chance at all, right? 1 in 4 is something that, it's like flipping a coin twice and getting 2 heads. It's like, that's not surprising. You're not doing anything magical with that. I believe you're probably still fair. And so there's no reason to give up on that hypothesis. Any questions? So the kind of the conclusion of this one, or men versus women's heart rates. We do not reject the null hypothesis. Means are equal. Because the observed difference is not unusual under the randomization distribution. The observed, or maybe you could say actual difference. 100 minus 98, about 2 beats per minute, is not unusual. do not reject the null hypothesis that the means are equal. I'm reading my own S here. Because the observed actual differences in the sample are very consistent with the sampling distribution under the null. It doesn't seem to cause us any concern. And so that is kind of the core idea of significance testing, right? In that we set up a hypothesis consistent with hypothesis. We look at the sampling distribution. Sometimes we can do it through randomization. And if our observed statistics are unusual, right, then we're going to reject the null hypothesis. What we'll do going forward is put formulas into this, so we don't have to rely on the computer, but use the standardized formulas. Because if under the null hypothesis we have some use of 0, and this is the sampling distribution of the sampling distribution of x bar, and it's roughly normal, and we observe, an x bar out here, under our assumptions about normality and all that, we can calculate this tail area probability. And we can do that under a normal distribution. We'll also do it under a t-distribution because we're estimating the standard deviations. And if that tail area probably is really small, like less than 5%, or less than 2.5% for the two-sided thing. Right? But if it's a small tail area, under the distributions, we can calculate, we're going to reject. Right? So we reject the null hypothesis. H0, we have the tail area probability is small. But we'll get more formal about that with formulas and discuss what it means and how it gets interpreted. But that's kind of the core part of hypothesis testing. And I like to do this randomization thing because I think it's good to think about what it means and instead of jumping into just a formula, because you can get pretty far into formulas and realize you're confused. So keep track of the main kind of core idea is how it's supposed to be working, and then see how it has to the formula is my recommendation. So that's good for today. Have a good weekend.
Wait, do we still have store credit from that app store?
Thank you. Thank you. So I'm going to sometime Friday night.
Sure, that'd be fine.
Yeah, I loaded my cart for laundry.
Oh, me too. I know.
Pack.
Where are you going?
Whenever I go to training, I gotta pack all my stuff up.
For what?
Whenever I go to training.
Have a good weekend.
Thank you.
Bye, Brandon.